what I taught you guys last week is dependent on three things, right? It dependent on the load application point or position. It can be also due to the change in geometry. It can also due to change in material. So in this question, I do apologize, I did not mention earlier, it's made up of the same material. Okay, so now we remove the support at point B, and we use the hangman theory. Okay, we use the hangman theory. Okay, so we look into, we're going to calculate over here, we're going to calculate delta L. Okay, we do. So delta L, we know that is equal to what? Is with the formula we're going to calculate, use is deflection is equal to PL over AE, right? And we also know that tensile is positive, compression is negative. Okay, so from here we calculate deflection of 1. Okay, deflection of 1. So deflection of 1 is going to sense the 300 and the 600. So this is equal to 300 times 10 to the power 3 plus by 600 times 10. Y is plus, is going to induce a tension. The area is equal to 250 times 10 to the power minus 6 divided by the cross-sectional. Hey, that is length, Eugene. Hey. Sorry, so this is the length. The cross-sectional area is 250 times 10 to the power minus 6. We are not given the Young's modulus, we just put E over there. Okay, because later on it will cancel out itself. So 900 power of 3 times 5.15 divided by 250 power of minus 6 is equal to 540 positive 540 times by 10 to the power minus 6 over E. And we know it's in tension, yeah? Because you remove the support at B. If you can also analyze when you remove the support at A. Okay, no problem at all. Either way, the answer will be the same. Okay. And you calculate the deflection of 2.
Sorry, you said if we remove it at 8, but wouldn't it be compression after
Yeah,
that?
will be compression. So you
Negative.
just flip it upside down. I mean, you just flip the figure, this figure upside down. Your answer will be the same. Okay.
Okay, thank you.
Okay. So deflection at point. So deflection at point 2 is not going to feel the 300. It's only going to feel the 600 in tension. So this is equal to the length, still 0.15, right? I think this part you all are very familiar how to do it now. Okay, E. So 600 power 0.3 multiplied by 0.5 divided by 250 power minus 6. So it's 360. Wait. 600 power 3 times 0.15 divided by 250 power minus 6. There's something in my calculator. Wait, 600 power 3 times by 0.15 divided by 250 power minus 6. So it's equal to, sorry, this is positive. Okay, I got it wrong. I don't know why I draw it negative. So this is 360. Okay, positive again, times 10 to the power 6. Okay. So it's equal to 360, positive 360, times 10 to the power 6, divided by Young's modulus. Okay. And then deflection at 0.3 is only going to see the 600, right? The 300 is on top, right? So at deflection at 3, it's only going to see the 600. The length is the same. Now the cross-sectional area changed to 400 times 10 to the power minus 6. Why minus 6 is because I changed to meter squared. Okay. And divided by E. So 600 by 400 power minus 6 is equal to 225. And then deflection of 0.4. This is so there's no load. I'm just going to write it out for you. So this thing is equal to 0. So now what we have calculated is we have calculated the deflection due to the applied load will be equal to delta 1 plus by delta 2 plus by delta 3 plus by delta 4. Okay. So this will be equal to 540 plus by 360 plus by 225 and then plus by 0. So this is equal to 540 plus 360 plus 225 is equal to 1125 times 10 to the power 6 divided by E. Okay. So we have formed, yes.
Could you please explain why for number 2 in section number 2 our P is 600, please?
Okay, because the 300 is on top of the 200, yes or no?
Correct.
So if we have the hangman theory, right? Right, your head is being pushed down by the 300 kilonewton, right? Your hands won't feel the 300. The answer is no, yes or no? Right, this part at this lower region will not feel the 300. The 300 is only felt at the neck.
Okay.
Okay, so it's I'm just applying the hangman theory, but it will feel the what? It will feel the 600, yes or no? Right, at section 2. So that's the only reason. Okay.
What about for diagrams that are sideways? That's like a silly question, but like I was trying to.
It's not a silly question. So diagrams, they are sideways, like what I've shown you before last week. We have a diagram that is it last week? Yeah, I think so. We have a diagram. I did an example last week, right? Oh, maybe not. So what you do is you just rotate the diagram, which I will show later on. Okay. Later on, we're going to solve a problem like this. Okay. So what we do is just rotate. Okay, we just rotate the diagram and there we go. Okay. Right.
Okay. Thank you.
So from here, okay. So from here, we know the load, right? So the next step we go do. So we know that we release the support at B. We allow the structure to extend. Okay. So we get this positive 11.225. So now the next thing is step 2. Right, step 2.
Sir, sorry to cut you off. The area that you're using, for example, like you know how it's already given to us, it's 250 millimeters squared.
Yes.
But that's for the whole thing. But you split it in two, though.
Yeah, because this is 250, this is 400.
Yeah, but you're supposed to split it in two, are you not? Or you use the whole area for section 1 and you use
I have to split into 4 because of these loads. Muhammad, does that make sense?
So you use
so the splitting is due to any of these: load applied position, change in geometry, or change in material.
Right. I understand that, but you see how for the first rectangle for the whole thing, for basically from A to C, it's 250 millimeters squared. But we're
Yeah.
using half of it. So
No, we're not using half of it. We have to section it into 4 points. 1, 2, 3, 4. Why we sectioned it 4 points? Because this area is the same but there's a change in applied load.
Right.
Okay, for that reason.
Okay.
Okay.
Yeah.
So now we look into step 2. Okay. We are going to introduce the redundant load at point B, right? Such that the deflection of the structure is equal to 0. Okay. So what we are going to do now, okay, I'm going to use the same. Okay, I'm not going to use the same diagram. I mean, the structure is still the same. So what we are going to do now is we are going to push the structure back. Right? So this is known as my RB. Okay. So you remove the rest of the load, right? Because you analyze the load, the applied load in section 1 already. Okay, step 1, you analyze the load. So now you remove the load. So where you see down here, you have point A, right? This is your point B, point C, point D, and then we have our point. No, there's no point D. Is there a point D? A. Oh, there's a D down here. D, C, and point K, right? Point D and point K actually has loads, okay? But we analyze them already. We remove them when we introduce the redundant load. Now, question for you. How many sections? 2 or 4?
2.
Well
2.
done. Right? Why only 2 sections? It is because section 1, right? We only need to divide this into 2 now. Okay, we only need to divide this into 2 now. 1. And why you divide them? Can someone tell me why is it only 2 sections? Anyone?
The shape.
Yes, there's only the change in geometry. Okay, one has an area of 250, the other one has an area of 400. Okay, so now we like to calculate the redundant, the deflection due to the redundant. Okay, so deflection due to the redundant of 1. Now, question for you. Now RB is pressing down from below, right? So section 1, what load is he going to see?
RB.
Yes. Think about the hangman. Okay. Think about the hangman. Okay. So now, if you are hanging over here, right? And I'm going to divide you into 2, 1 and 2. If at your feet I push up, okay, I push up RB, right? You're going to feel RB in your hands, are you? Right, at your elbow. That's why you can do the push up, right? You can do the chin up, yes or no? Right? And then if I push RB here, and if we have a knee, if you don't stiffen your knee will bend, yes or no? Because it's feeling the RB. right? So I want you all to have this sort of visualization in your mind, okay? Because this sort of visualization will help you in your analysis, okay? And well done, okay? So it's going to induce a compression RB. The length over there, we know that is equal to 300. The cross section, oh, not 300, come on, Eugene, in meters, 0.3. And then we know that the cross-sectional area is 250 times 10 to the power minus 6. And then we know that this is E. Okay, so 0.3 divided by 250 power minus 6 is equal to 1200. Wait, 0.3 divided by 250 power minus 6 is equal to minus 1200, right? RB over E. Then the deflection due to the redundant load at 2 is also going to induce a compression, RB. The length is 0.3 and the cross-sectional area is 400.